So in this video, we are going to look at paper 2 question 3s for the June CSEC math exam for the years 2022 to 2019. So here we have our first question for June 2022. So this is question 3 for June 2022. We have the diagram below shows 4 shapes, P, Q, R, and S. So here we have P, Q, R, and S on a square grid. So this is just the Cartesian plane, your y-axis and your x-axis. And part A, we want to describe fully the single transformation that maps the shape P onto the shape for part 1, which will be Q. So basically, we just want a single transformation that's going to map the shape P to Q. So let's locate those two shapes. So here we have shape P and shape Q like this. Now, remember, we just have 4 transformations. All right, we have a translation. Now I'm going to demonstrate what is a translation with a shape here. So a translation is simply shifting the shape about. All right, so you shift it a certain amount of units up and across or down and across. You know, any combination of that, that's a shift. All right, so notice when you shift the shape, the orientation of the shape remains the same. Now, if you look at P and Q, the orientation is different. So therefore, it's not a translation. If the transformation from P to Q was a translation, then the orientation will remain like this. All right, and you'll just be shifting this shape somewhere about on the Cartesian plane. But here you're seeing that the orientation is different from P, so it's not a translation. All right, next we have a reflection. Now, the thing about a reflection is that the image is be laterally inverted. So if P was to be laterally inverted, it would look like R. So R is basically a reflection of P in some mirror line, right? Because it's these two shapes here, well, R is laterally inverted from P. So this is what we call lateral inversion. So obviously Q is not like that. So the transformation between P and Q is not a reflection. The next type of transformation you have is what we call enlargement or reduction, right? So enlargement, I'll demonstrate with the shape here. All right, would mean you make the shape bigger, that's enlargement, or smaller, that's a reduction. But notice in making it bigger or smaller, all right, the orientation remains the same. All right. Now notice between P and Q, the size is about the same. The orientation is not the same. Okay, so it's not an enlargement. So those 3 transformations are out, which leaves the last one, which is a rotation. So by a process of elimination, we'll say that, okay, the transformation between P and Q would be a rotation. So if it's a rotation, you need to find what is the center of rotation and what is the, whether it be clockwise or anti-clockwise, the direction, and the angle of rotation. Okay, how much degrees clockwise or how much degrees anti-clockwise. Now, in order to do that, I need to draw lines to the corresponding points on both diagrams. So this point here on P would correspond to this point here on Q. This point here on P would correspond to this point here on Q. This point here on P would correspond to this point here on Q. And this point here on P would correspond to this point here on Q. And of course, the last one we have this point here in black here corresponds to this point here on Q. Now we don't need to draw lines to connect all these points. All we need is 2 lines. So I'll choose the green. So I'll draw a line like this, connect these 2 points, corresponding points. And notice if I connect the brown, it will be like this. If I were to connect the red, it would be like this. Now notice these 3 lines, they intersect at the same point. So if you connect the black, you'll see it passes through that same point as well. All lines intersect at that same point. And the blue would just be an extension of the black. All right, so it will pass through this point as well here. So this tells me, all right, now normally what I would do is connect this 2 lines, all right, and then I'll have to bisect the 2 lines, and where the perpendicular bisectors meet would be the center of rotation, and then you take a protractor and measure the angle, okay? But this is a special case here where when you connect the lines, all the lines, they're intersecting at the same point, so that would be a rotation of 180 degrees. Could be clockwise or anti-clockwise, and this point here would be center of rotation. So this would be 7 on the x-axis and 7 on the y-axis. So the coordinate 7, 7 would be the center of rotation. So I'll put I'll just put clockwise, rotation of 180 degrees about center of rotation 7, 7. And this is your single transformation to describe the transformation that maps P onto Q. Now let's look at part 2, where we want to find a single transformation that maps P onto R. All right, so this is P here and this is R. And as I mentioned before, that this image here is laterally inverted from P. All right, therefore this would be a reflection. So you see, same size, that's the image is inverted. So what we have to find is what is the midpoint between R and P, and that will be our mirror line. All right, so let's start to count here. I have 1 block, 2 blocks, 3, 4. 4 blocks, right? So about 2 blocks, that would be our midpoint, and our mirror line will be this straight line coming down here. All right, so for part 2, this will be our mirror line. All right, because it's directly in the middle of P and Q, because that's the condition for reflection, right? The distance between the object and the mirror line must be the same as the image and the mirror line. So if this point here is 1, 2 away from the mirror line, then this point here must be, then the object must be 1, 2 away from the mirror line. All right. So the mirror line here is the line x is equal to 1. All right, so I'll write that x is equal to 1. That's the mirror line. All right, so R is a reflection of P in the mirror line x is equal to 1. And that will be a single transformation that will map P onto R. So I'm going to put a reflection in the line x is equal to 1. And that's because this line will come down and touch the x-axis at 1. All right, so that's why it's called x is equal to 1. Now for part 3, we want to describe a single transformation that will map the shape P onto S. So this is P here and this is S here. Now we can clearly see that the orientation is the same, but S is bigger than P, so this is going to be an enlargement. So for enlargement, we need to find the point of enlargement and also the scale factor. Scale factor just means how much times bigger S is than P. So what we'll do is connect lines to our corresponding points on both shapes. So I have this point here in green on P. The corresponding point will be here on S. I have this point here in blue on P. So this corresponding point on S will be right here. Likewise, this point in red here on P will correspond to this point right here. This point here on P, which is in brown, would correspond to this point down here. And of course, this point in black here will correspond to this point here. All right, so now what we'll do is connect the corresponding points like this, and we'll extend the line. All right, so connecting the greens and extending the line. Then I'll connect the blue. Also extend that line. Connecting the red now. Gonna connect the brown. Now all we needed was 2 lines, but let's do a little extra just to demonstrate the point. You see all lines intersecting at this point. Now this should be about, I know this line is sort of faded, all right, but this should be about 11 here coming across. So 11, all right, on the y-axis and the 7 on the x-axis. So the coordinate for this point will be 7 and 11. So this coordinate here, marked with an x, will be 7 and 11. All right, so this would be your point of enlargement. All right, and now we just have to determine how much times bigger is S than P. Now we could count it by looking at the corresponding sides. All right, so we could say, okay, this here is 1 block. So on the object here, this here is 1 block, and on the image, this is 2 blocks. So right now, looking like S is 2 times P. All right, let's confirm again. Here we have 2 blocks, and here we have 1, 2, 3, 4. So again, this showing that S is twice P. Now let's look at this side here on both shapes. All right, so we have on the object, we have 1, 2, 3, 4. And on the image, we have 1, 2, 3, 4, 5, 6, 7, 8. So again, it's showing that S is twice P. So that would indicate that the scale factor is 2 because S is twice P. Now, another way to do it is to measure it with your divider. Now, I do have a divider here, but I have a compass, which we could use that in place of the divider. All right. So if I bring my compass here and let's go from the point of enlargement, and let's say I measure the line in green. I open the compass out to measure the distance. So that's the point in green from the point of enlargement. And I'll call this a scale factor of 1. And as I move the compass point here now, all right, see it lines up perfectly like that. That'll be a scale factor 2. Okay, let's check another point. Let's do the one in blue. All right, so from the point of enlargement, let's line it up with the blue. All right, so this is a scale factor of 1. All right, and as I move the compass point here now, see it lines up here. So that's now a scale factor 2. All right, so that's what I can do to the divider or compass. All right, so that's how we know the scale factor is 2, like that as well. So I'll put an enlargement of scale factor 2 with point of enlargement, and that'll be this coordinate here, 7, 11. So now for part B, we have on the grid provided, which is this Cartesian plane here. We want to draw the image of shape P, so that's shape P here, after a translation vector -2, 3. I'm going to label this image T. Now let's look at the translation vector -2 and 3. Now this -2 here will be the x component, and the 3 here will be the y component. Now the x component of the vector would control the horizontal distance, all right, because the x-axis is a horizontal line, and the y component of the vector would control the vertical distance, and that's because the y-axis is a vertical line. Now because the x component is -2, that will mean 2 spaces going to the left. Notice here negative numbers are on the left side of the Cartesian plane for your x-axis. So -2, 2 units to the left, all right, horizontal, right? And if it was +2, you move 2 units horizontal to the right, all right? Now this is +3 on the y, so that means 3 units upwards, okay? And if it was -3, that'd be 3 units downwards, okay? So what we are doing is moving 2 units to the left and 3 units upwards. So what we're going to do is take all the points on P and translate it 2 units to the left and 3 units upwards. So starting with this point here, we count 2 units to the left, 1, 2, and then 3 units upwards, 1, 2, 3. So that's here. Then we can take this next point here, and we go 2 units to the left, 1, 2, and 3 units upwards, 1, 2, 3. That's here. All right, then we can take this point in here, right? 2 units to the left, 1, 2, and 3 units upwards, 1, 2, 3. That's here. Then we can take this point here, 1, 2 to the left, and 3 upwards, 1, 2, 3. So that's here. Then I'll take this point here and go 1, 2 to the left, and 3 upwards, 1, 2, 3. So that's here. All right, so I'll put this last point in brown because I run out of colors. And with 1, 2 to the left, and 3 units upwards, 1, 2, 3. So that's here. Now, okay, let's connect those points and make our shape. And we're going to call this shape T. All right, so we have translated this object P to form this image T with a translation vector -2, 3. All right, so that's mean 2 units to the left, 3 units upwards. So now we are moving on to question 3 for June 2021. So for part A, we have the diagram below shows the triangle PQR, in which angle QPR is 62 degrees, that's this angle here. Angle PQR is 90, that's this angle here. And the PR is 11, that's the side here, PR is 11 centimeters. Now they want us to calculate the size of angle PRQ. So the vertex of the angle is always the letter in the middle, so that's the angle will be at R. So P to R to Q, so the angle is at R here. So I'll just mark off the angle that we want to find here. And now remember, the sum of the interior angles of a triangle would add up to 180 degrees. So therefore, this angle here, which is PRQ plus the 62 degrees plus 90 degrees, must be equal to 180 degrees. So I'll write angle PRQ plus the 62 degrees plus the 90 degrees would be equal to 180 degrees. So now angle PRQ. 62 plus 90 is 152. So plus 152 degrees is equal to 180 degrees. So now when I transfer this positive 152 degrees across the equal sign, I would have angle PRQ is equal to 180 degrees, take away 152 degrees. And therefore angle PRQ would be equal to 28 degrees. So I'll just write 28 here, so 28 degrees here. So moving on to part 2 here, we want to find the length of the side RQ. So this is RQ here. So this is a right angle triangle. So we know that Pythagoras theorem and the trig ratios applies to the right angle triangle. Now to use Pythagoras theorem, you need a right angle triangle. You need to know two sides and one side missing. So you'll use Pythagoras theorem to find the missing side. Now here we just have the length of one side. Therefore we cannot use Pythagoras theorem. So we have to use the trig ratios. Now to use the trig ratios, you'll label the triangle with respect to one of these angles, either the 62 degrees or the 28 degrees. So I will go with the 62 degrees. So the side opposite the 62 degrees will be called the opposite side. So this here is your opposite. The side opposite the right angle would be your hypotenuse. So this would be a hypotenuse here. And the remaining side will be your adjacent side. So now I'll say so ka toi, so ka toi. Alright, and that simply means sine of your angle is opposite over hypotenuse, cosine of your angle is adjacent over hypotenuse, and the tan of your angle is opposite over adjacent. Now see that we want to find RQ, and RQ is the opposite side, our formula must have opposite in it. So sine has opposite and tan has opposite. Cosine doesn't, so cosine is automatically out. Now, when we're using the trig ratios, we have three variables, the angle and the two sides. In an equation, you can only have one unknown. Alright, so seeing that we already know the angle that we're using, which is the 62 degrees, alright, and the unknown will be the opposite side, then the next side that I choose, I must know the length of it. Alright, so do I know the adjacent? No. So if I use adjacent and opposite, which will be tan, I would have two unknowns, and that's why I cannot use tan here. So the other side that I know would be the 11 centimeters, which is the hypotenuse. So I'll be using opposite because I need the opposite because that's what I want to find. And I have the length of the hypotenuse. So what ratio has both opposite and hypotenuse in it? That will be sine. Sine is opposite over hypotenuse. So I'll write sine of my angle, which is sine of the angle, which is 62 degrees, is equal to the opposite side over the hypotenuse. All right, let's put in those variables. So sine of 62 degrees is equal to my opposite, which is RQ, over my hypotenuse, which is 11 centimeters. So now I want to cross multiply here. So I'll put the sine 62 degrees over 1. And I'll put back here my RQ over 11. So now when I multiply 1 times RQ, I will simply get RQ. And when I multiply sine 62 degrees by 11, I will get 11 times sine 62 degrees. Alright, so this means 11 multiplied by sine 62 degrees. Now on a calculator, I can put in 11 multiplied by sine 62 degrees, or I could just put 11 sine 62. So using my calculator, I'll put in 11 sine 62 degrees. Now make sure the DG is on your calculator before you calculate the answer, because if it's not, you'll get the wrong answer, because we are using angles in degrees here for this question. So I press equal and I'll get 9.712. So I'll write that to three significant figures as 9.71. So I'll have RQ is equal to 9.71 centimeters. So now moving on to part B of this question, we have the diagram below shows three triangles, X, Y, and Z. And for part 1, we're saying that triangle X is mapped onto triangle Y by a reflection. State the equation of the mirror line. Alright, so X is mapped onto Y by a reflection. I can see that both X and Y are laterally inverted, so you know it's a reflection. Alright, so remember the distance between the object and the mirror line must be the same as the distance between the image and the mirror line. So you just need to find the halfway point between X and Y. So let's count from this line here. We have 1, 2, 3, 4 blocks. So the halfway point will be 2 blocks, right? So 1, 2. So essentially, mirror line is going to be the x-axis. Now notice this says state the equation of the mirror line. So yes, the mirror line is the x-axis, but that's not the equation of the mirror line. So this is 0 on the y-axis, and the x-axis passes through the 0 on the y-axis. So this is the line y is equal to 0. So the x-axis is the line y is equal to 0. So y is equal to 0 is the equation of our mirror line. Now for part 2, we want to describe fully the transformation which maps triangle X onto triangle Z. So this is triangle X here, and this is triangle Z here. So obviously the orientations are different. And I previously went through the 4 types of transformations. Okay, both the enlargement, the translation, the orientation remains the same. The reflection is laterally inverted. And then you have the rotation. So since this is not laterally inverted, Z and X, they're not laterally inverted, there's not a reflection. Z and X looks like the same size, so it's not an enlargement. Okay, so it has to be a rotation. So what we'll do now is connect the corresponding points. This point here at 2 would correspond to this point here. This point here would correspond to this point here. And this point on top here would correspond to this point here. Now, say all we need is 2 lines. So I could connect these 2 points like this. And then I could connect these 2 points like this. And then I could connect these 2 points like this. Now notice I have a situation here where all 3 lines not intersecting at the same point. So this is not going to be a rotation of 180 degrees. So what I'll need to do is just take 2 of the lines and bisect it, construct the perpendicular bisector. And where the perpendicular bisectors meet would be a center of rotation. So I'll need my compass for this. And if I choose to go with this line here first, I need to open my compass out to more than half this line. So let's see. Place my compass point here. Make compass smaller. This is the smallest I can make the compass. So what I'll do now is make an arc like this. Then I'll place the compass point at this point. And make an arc like this. And now I'll make a line to connect where these 2 arcs intersect, here and here. Alright, so that'll be this line here. So now you can see that this here is the perpendicular bisector of this line. It's exactly at 90 degrees to this line here. Alright, so now I'll do the same thing with either this line here or the one in green. So now let's choose any one you want. I'll go the one in green. Alright, so I'll get my compass again, place it at this point here, open my compass out to at least more than half the line. This should work. Alright, so I'll make an arc like this. Then place the compass point down here. And I'll make an arc like this. So now I'll draw a line connecting these 2 points at intersection where the arcs intersect. So now I'll draw my line like this, and I'll draw it straight down to intersect the line in blue. So here I have my perpendicular bisector of this line in green. And notice I draw it straight down to intersect the perpendicular bisector of the line in blue. And both of these lines, they intersect at the origin 0, 0. So this would be my center of rotation. Alright, so I'll just highlight in here with an arrow that here's the center of rotation, 0, 0, the origin. Alright, so we found our center of rotation. Now, seeing that X is the object and Y is the image, the rotation is going in a anti-clockwise direction. So let's put in red as well. We are going in a anti-clockwise direction. Now, in order to find the angle of rotation now, I need to connect like any 2 corresponding points, draw a line from that point to the center rotation and from this point to the center rotation. Now, since I already have blue and green with the bisectors, I'll use the one in brown. All right. So I'll connect this point here in brown to my center of rotation here. And then I'll connect from my center rotation to this point here in brown. All right. And now I'll measure the angle here. Now, just visually, you see this looking like 90 degrees. But I'll get my protractor and just make sure. All right, so just going to line up the center of the protractor with the center of rotation. And make sure this 0 line lines up with the line. All right, this 0 line lines up with the arm of the angle. So this is my angle here. My 2 arms. All right, so this line here on the protractor lines up with one of the arms of the angle, right? And that must be a 0 on the protractor. So I would not be using the inside scale because this line will line up with 180 degrees on the inside scale, and I wanted to line up with 0. So I'm using the outside scale. And if we go all the way around from the outside scale, starting at 0, all the way around to this line here, you see we get 90 degrees. So we have an anti-clockwise direction. The angle here is 90 degrees, okay? And the center rotation is the origin. So to describe this transformation fully, I'll say a rotation of 90 degrees anti-clockwise about the origin. All right, so this is the thing about rotation. To get the angle of rotation and center rotation and stuff like that, things get pretty jumbled up. All right, but that's the nature of it. All right, so what I'll just do is just try and highlight this 90 degree here. All right, so this is my angular rotation here, 90 degrees. So I'll put a little box here. So now for part 3, this is on the same diagram. They want us to translate y using a vector of -7 and 1. So you know -7 is going to be our x component, and negative means go to the left 7 units, and 1 is the y component, which means to go up by 1. So you're taking y and we're translating that 7 units to the left and 1 unit upwards. And we're going to label this image phi. All right, so if you start with this point here, right, you're going 7, 1, 1, 2, 3, 4, 5, 6, 7. 7 to the left is -7 and 1 upwards. 1 upwards, that's here. All right, we take this next point here. Go 7 to the left. 1, 2, 3, 4, 5, 6, 7, and 1 upwards. That's right here. And then we take this last point here and go 7 to the left. 1, 2, 3, 4, 5, 6, 7, and then 1 upwards. That's here. And we just connect the points now. And we're going to label this image phi. All right, so this is your translation. We translate y as the object to get this image phi. All right, so that's part 3. So now moving on to part 4, they say on the diagram, all right, on page 10, which will be this diagram here. All right, enlarge triangle x. So this is triangle x here, about the center 0, 0, which is the origin, and the scale factor is a half, and label this image w. Now we've seen that how things just jumble up here. I'll just take probably a fresh diagram of this, and do this on a separate page. So here we have our diagram for part 4. So we want to enlarge triangle x about the center 0, 0, which is the origin, and have a scale factor of a half. I'm going to label this image w. All right, so I'm just going to highlight what is our point of enlargement, which will be here, the origin. So what we'll do is draw straight lines from a point of enlargement, which is the center, straight through the points on the shape. So that's like here, so. And here. And what we want to do is find half of the distance. So from this point here to this point was half, that'll be in the middle here. Okay, so let's use green to make that. So this first point gonna be here. All right, then we're gonna measure this distance from here to here and find half. And same thing, this distance from here to here and find half. Now what I could observe is on this line between this point here and here, this diagonal is between these 3 boxes here, and then this diagonal is between these 3 boxes here. So halfway is going to be right here. All right. So what I can observe between this point here and this point here is that about here is the halfway point for this line. So that will be right here. All right. You can clearly see this passes through 2 boxes. This is the diagonal of 1 box, 2 boxes, diagonal of 1 box, 2 boxes, so halfway. All right, same thing here. Looking at these 3 boxes here, straight diagonal here. Look at these 3 boxes here, diagonal here, so halfway. All right, the other thing you can do is that since the halfway point for this one was easy to get, all right, which will be here, is that's obvious. What you can say is since it's a half, take the length at this side here now, and let's find half of it. So this is 1, 2, 3, 4, 5, 6 blocks. So from this point, you're going to go 3 blocks instead. 1, 2, 3. All right, so we know we'll be accurate here. All right, and from this point, you have 1, 2 blocks. So half of that's going to be 1. All right, so you know it's going to be 1 block upwards that had to touch this line. All right, so that's why it's going to be this point. So now we just connect our points like this. All right, and this will be our image W. All right, so just remember scale factor of a half. This means that this image has to be half the size of this object X. So moving on to question 3 for June 2019. Here we have a construction question where we have to use our ruler, pencil, and a pair of compasses only to construct a triangle, NLM, in which LM is 12 centimeters. So I'll draw this first. All right, then we have the angle at L will be 30 degrees. Right, remember the angle, your vertex of your angle is at the letter in the middle. So MLN, angle MLN is 30. So angle at L is 30. And angle LMN, so the angle at M is 90 degrees. So first I'll take my ruler, place it anywhere on my page. Well, I'm assuming that my triangle will come somewhere on top here, right? So just make it a little low. And I'll draw a light line that's more than 12 centimeters long. Then I'll take my compass, place it on my ruler, place the compass point at 0 and open out the compass to 12 centimeters. Then I'll place my compass point at any point on the line. And I'll make an arc like this. And where the arc cuts the line like here, I'll place the compass point there. And I'll make another arc like this. So between these 2 points will be L and M. All right, so I have my line segment, LM, which is 12 centimeters long. So as I said, at L, we will be constructing a 30-degree angle. So that's at this point here, we'll be constructing a 30-degree angle. First, I'll need to construct a 60-degree angle. So I'll open the compass out to a distance that I'm comfortable with. I'll make an arc like this. Where the arc cuts the line, I'll place the compass point there and make an arc like that. Then I'll draw a line from L straight through that point of intersection, and that will be our 60-degree angle. Now remember, I want 30 degrees. So that means I have to bisect this 60-degree angle. So what I'll do is, seeing that I have my compass point at this point here, I will just extend this arc like this. And I'll place my compass point where the arc and the 60-degree line intersect. And I'll make an arc like this. And this line here will be my 30-degree line. So now I have to construct 90 degrees at M. So I'll open my compass out at a distance that I'm comfortable with again. Place my compass point at M. I'll make an arc like this. Where that arc cuts the line, place my compass point there. Make an arc like that. Where those two arcs intersect, place the compass point there again. And I'll make an arc like this. And where these two arcs intersect here, place the compass point and make an arc like that. Okay, so what I'll do now is connect this point here where these two arcs intersect and M, and that will be my 90-degree angle. Now the point where my 90-degree line and the 30-degree line intersect, that will be the third point on your triangle, which will be N. All right, so you already have L and M, so N would be on top here. So now once you're happy with the diagram, we'll darken the final outline. So all these lines were drawn lightly. All right, those are your construction lines. All right, and once you're happy with your diagram, you darken the final outline. And that's it. We have our triangle NLM. All right, so here we are moving on to part B of this question, where we have triangle ABC with vertices A is 1, 1, B is 1, 4, and C is 3, 1. All right, so that's your A, your B, and your C. All right, so here we want to show that triangle ABC's map onto triangle LMN by reflection in the x-axis, followed by a reflection in the y-axis. So this is our triangle ABC. We're going to reflect it in the x-axis first, and then in the y-axis. All right. So for part 1, we're going to draw that and label that triangle LMN. Now, if this is our mirror line here, the x-axis, the distance between our object and the mirror line must be the same between the image and the mirror line. So if this is the object A here, then the image would be right here. All right, because the distance between the object and the mirror line must be same as the image and the mirror line. And of course, the line connecting the object and the image must be at right angles to the mirror line. So my object C here, the image will be one block away from the mirror line here. So the image is 1 block away. And my object B up here is 1, 2, 3, 4 blocks away. So that'll be 1, 2, 3, 4 blocks away, the image here. All right, so I'll connect these points. But remember, we're not done here, right? Because remember, it's a reflection on the x-axis followed by a reflection in the y-axis. So this is the reflection on the x-axis. Now I must reflect this in the y-axis. So this is the y-axis here, and we're doing the same thing. So this point in red here is 1 block away from the y-axis, so 1 block away like this. Of course, the line connecting the image and the object must be 90 degrees to the mirror line. All right, if this one is 1, 2, 3 blocks away, so 1, 2, 3, that's here. All right, and then this one here is 1 block away, so this is 1 block away here. All right, so now we'll connect our points. All right, so this will be our final image here. So notice to say ABC is mapped onto LMN. So that means A is mapped to L, B is mapped to M, and C is mapped to N. So the A is in red, so that will be L here. So this will be L. We have the B in brown. All right, so that this will be LM, so M down here. And of course, the next point is going to be N. Now here it's saying describe a single transformation that maps ABC to LMN. So what maps this triangle to this triangle? Now we discussed the 4 types of transformations already. And we can see that LMN is not in the same orientation as ABC. So obvious thing that we're looking at is not laterally inverted as well. So it's going to be a rotation, right? So we're going to connect the corresponding points. Okay, so we connect L to A. All right. Then we have N to C. And then we have M to B. Now you can see all 3 lines intersect at the same point. And when that happens, we know it's going to be a rotation, whether it be anti-clockwise or clockwise of 180 degrees. And where it intersects would be a center rotation. So it's intersecting at the origin. So the origin is our center of rotation. So for part 2, we're going to have a rotation of 180 degrees, as for clockwise, about the origin, right? The origin is 0, 0. Now for part 3 of this question, they want to state a 2x2 matrix for the transformation that maps ABC onto LMN. Now remember, the transformation is a rotation of 180 degrees, whether it be clockwise or anti-clockwise, about the origin. All right. So we're supposed to know that that 2x2 matrix is -1, 0, 0, -1. All right, so my 2x2 matrix which represents the transformation would be -1, 0, 0, -1, like that. So it means if you multiply this transformation matrix by the object coordinates, you would get the image coordinates. All right, so I'm just going to put a little note here. All right, if I multiply -1, 0, 0, -1 by my object coordinates. Let's say the coordinates are A, which is 1, 1. So let's put 1, 1 here. I will get the image coordinates, and A being 1, 1 corresponds to L here, which is you're not seeing this point here, but it's supposed to be -1 here, right? -1, and here will also be -1. So this will be -1, -1. If you do the matrix multiplication. All right, so this is A, coordinate A. This is L, the image, and this is my transformation matrix. And if I do that same thing for all 3 points, I'm supposed to get the coordinates for the image. If I multiply the transformation matrix by the object coordinates like this, I'm supposed to get the image coordinates. And that's it for this video.